All right. Okay, so welcome back after a week-long hiatus. Let me start by just sort of recalling where we were, because we were sort of halfway through analyzing an algorithm for some setting, and now it's been a week, and like who knows what the setting was or what the algorithm we were analyzing was. So the setting was this sort of online linear optimization problem. And if you recall, there was sort of this motivating, maybe instantiation of this, which was that maybe we have a really large action space. Maybe we're choosing routes to drive along in a road network, for example. I start at some node in the graph S. I want to get to some node in the graph T, and the set of all paths between S and T in the graph are feasible actions for me. Okay, so this is like a really huge, it's a really huge action space. The number of paths between two vertices in a graph could be exponentially large in the number of vertices in the graph, for example. But it's a setting where the cost for each of my actions can be computed from a relatively low dimensional summary statistic. You don't have to separately tell me the commute time along each path in the graph. It is enough that you tell me the commute time along each road segment in the graph. And then if I want to figure out the commute time for a path, I just add up the commute times along the corresponding road segments. Okay, so this is a sort of problem with a big action space, but one in which my payoff function has a low dimensional linear structure. If I want to know what is my cost for an action, which is a subset of roads in a road network, I sum up my costs along each of those road networks. Okay, so the number of paths is really big. The number of road segments is manageable, and I can figure out the cost for each one of my paths if you just tell me the cost for each of the road segments. Okay. And so the sort of formalization of this problem, which is much more general, but for which this sort of online shortest paths problem is a special case, is this problem that we called online linear optimization. Okay, so in the general problem, the learner has some arbitrary action space embedded in R to the D. So each of their actions is a D-dimensional vector. Okay, the action space could have structure. So for example, to encode the online shortest paths problem, the set of feasible vector, D would be, first of all, the number of road segments on the map, okay, the number of edges in the graph. And the action space would be binary valued vectors that correspond to indicator vectors for whether a particular ST paths in the graph include an edge or not. So there'd be one action for every path, ST path in the graph, and I could represent these as vectors indicating which edges are present in that path and which are not. Okay, similarly, the adversary has an action space which also consists of vectors in R to the D. Here, for example, this would be sort of the adversary could choose a congestion independently for each of the networks in the graph. If we wanted, the adversary's action space could also encode some structure. Maybe feasible congestions have to satisfy flow constraints or something. And then what happens in rounds is the learner chooses an action. Actually, they're allowed to randomize, so they can choose something in the convex hull of their set of actions. I can choose a probability distribution over paths. The adversary chooses a cost vector, like a congestion for every edge. And then the learner's cost, in the end, it's the inner product between these two things. So this is what's encoding the sort of low dimensional linear structure that the online shortest paths problem has, which is the structure that we sort of hope to take advantage of here. Okay. This is, like only more general than sort of like the expert setting where we're just choosing amongst K actions. That setting is the special case where your actions are just sort of like the D standard basis vectors. And if we remember, like the hope here is that even though the action space is really big, we can take advantage of this linear structure to give algorithms that have regret guarantees that are hopefully comparable to those we got from multiplicative weights that depend only logarithmically on the number of actions, but that are feasible to run even when the number of actions is really big. Okay, and just sort of one more thing about the model. Remember, this is a general enough model that it can encode problems in the online setting that would be computationally hard even in the batch setting. So for example, if I said, okay, every round, you're not going to choose the shortest path in the network. What you're going to choose is the cheapest Hamiltonian cycle. Okay, so like the cheapest cycle that visits every vertex once and minimizes costs. Well, that would also be an instance of online linear optimization. We could get information theoretically good regret bounds for that problem, but it would be too much to hope for to be able to solve that problem with a polynomial amount of runtime, because the sequential version of the problem we've presented here is only harder than the one-shot version of the problem, and it's an NP-hard problem. And so, like, how are we gonna? And yet, like, our sort of goal is to come up with efficient algorithms for solving this problem in generality, right? And so, like, how are we gonna reconcile those two things, that we want to solve this general class of problems, but this general class of problems includes things that are computationally hard? Well, what we're going to do is we're going to give algorithms that are essentially efficient reductions to the problem of one-shot optimization. Okay, so for online shortest paths, like, our algorithm will end up basically making a small number of calls to Dijkstra's algorithm for computing shortest paths in a fixed graph. That's an efficient algorithm. If I wanted to solve some kind of online Hamiltonian path problem, what I'd have is, an efficient reduction to, calls to an algorithm that solves fixed Hamiltonian path problems, but that wouldn't, I wouldn't have an efficient algorithm for doing that. Okay, and so formally, the way you should think about what the algorithms we present here as reductions from the online problem to the batch problem. Formally, the way that will manifest itself is that in the algorithm, it is going to be okay to assume that we can solve this fixed maximization problem. Given a vector of costs, given any vector of costs, we're going to assume that we can say, okay, well, find me the action that minimizes the inner product between the vector representing my action and the costs. Okay, and so whenever that optimization problem is easy, our algorithms will run in polynomial time. Okay, everyone remember the basic premise? Cool. Okay, and so then let's remember the actual algorithm that we're gonna analyze. Maybe I'll write it over here because it'll be nice to keep it on the board while we do the analysis. Okay, and it's called Follow the Perturbed Leader. We started looking at it last time. I'll call it FTPL for short. And it's actually like a super simple algorithm. Okay, so all that happens is sequentially from round little t1 to big T, we look backwards in history and we see what are the cost vectors that our adversary has chosen to materialize cumulatively from rounds 1 up through t-1. So the historical cost up through and including yesterday. Okay, and we sum those up. Let's call that vector c less than t to denote that it is accumulating all of the costs we've seen up through, but not including today, including yesterday. Okay, so this is just the sum over all of the rounds from day 1 through t-1 of the cost the adversary chose at that round. And then we will flip some coins. We'll sample some noise, basically. And we're just going to sample it from a uniform distribution. Okay, so we'll let nt be drawn. It's going to be a vector of length d. It's going to be, every coordinate in that vector will be drawn uniformly between 0 and 1 over epsilon, where epsilon's a parameter. We'll prove a theorem in terms of epsilon, and then we'll set epsilon optimally. Okay, so we have this d-dimensional vector of accumulated costs. The accumulated costs so far. We've got similarly this sort of d-dimensional vector of just uniformly random noise. And all the algorithm is going to do is it's going to select the action AT, that is the action that minimizes the inner product between A, the vector representing the action, and the accumulated vector of costs perturbed by the noise. Okay. So it is doing something pretty straightforward. If you recall last time, before we wrote down this algorithm, we wrote down maybe a more straightforward algorithm that was just called follow the leader and didn't add the noise. Okay, that would be like a really obvious thing to do. Like you're trying to compete with whatever action turns out to have done the best in hindsight at the end. Well, we don't know what that's going to be because we don't know what the future holds, but we do know what is the best action. We do know what is the action that, had we played it consistently, would have performed the best in hindsight if play stopped today. That would just be the action that minimizes the inner product with the accumulated cost vector. Okay, and so if we weren't adding the noise, we would just be every day playing the action that would have done the best in hindsight had we played it every single day. And that's like a natural algorithm, but we sort of saw it didn't work. We gave this sort of bad example where what we did is we sort of chose an alternating set of cost vectors where basically action 1 was expensive, then action 2 was expensive, then action 1 was expensive, then action 2 was expensive, which sort of kept the best action in hindsight sort of on this knife edge. Like on even rounds, action 1 was the best action in hindsight. On odd rounds, action 2 was the best action in hindsight. And playing Follow the Perturbed Leader was sort of, like using like a bad tie-breaking rule. Like there were never actually ties, but it was always, almost a tie. And Follow the Leader always played the high cost action. Okay, so like the best action in hindsight, had cost T over 2, but Follow the Perturbed Leader always chose the wrong thing and it had cost T. That wasn't good. And sort of the intuition for, and this is almost the same algorithm. It's doing that. It's just, adding noise. And you can think about what the noise is doing. Is it sort of like causing the algorithm to randomize when there are ties? Like when there's two things that are sort of almost equally good within the margin that the noise can, put any of them over the edge, this algorithm will randomize and sometimes play each of those actions. Okay, and sort of it's clear that that would break the bad example we saw last time, where, what we were arranging to do by having these sort of alternating vectors of costs was we were making sure that like action 1 and action 2 had almost the same cost in hindsight. And so if we added, any non-trivial amount of noise, Follow the Perturbed Leader would basically pick uniformly at random between those two actions every day, which on that particular sequence actually would have done great. And what we want to prove is that, somehow like that was actually the only bad case. Like we can actually, this algorithm in a fully general setting has a good regret bound. Okay. So the theorem, which we wrote down last time but didn't finish proving, was this: the expected regret of Follow the Perturbed Leader to each action A is bounded as follows. Okay, so what are we looking at? We're looking at the sum overall time of the expected cost of the algorithm. So this is, what is the expectation over? Well, it's a randomized algorithm. So we're choosing, we're sampling these sort of noise random variables uniformly. That's what the expectation's over. The expected cost of the algorithm, so the expected inner product between the action chosen by the algorithm and the cost chosen by the adversary, minus the cost that we would have experienced had we played the same fixed action A every day. Okay, this is, we're claiming something for all A simultaneously. So if we can show this is small, this will mean that our cost is nearly as good as the best action in hindsight. We claimed that this was going to be bounded by, all right, I'm going to write down a lot of letters. I need to tell you what they are. A over epsilon plus 2 CRT epsilon. Okay, what the heck is that? Well, A is like the diameter of the action space. It's like how far apart, as measured by L1 distance, are any 2 points in the action space. Okay, right, 2 points in the action space are vectors. I'm interested in, like, how different they can be, how big they are, basically. Okay, so like if we were encoding the experts problem where the actions corresponded just to like standard basis vectors indicating which action we're playing, this would just be 2. If we're looking at the shortest path problem, this would sort of look like the twice the length of the longest path in the graph. And more generally, it's sort of clear that we need some term like this that sort of captures the scale, because like if I just multiply everything by 10, all of the numbers involved, and therefore the regret will go up by a factor of 10. So like the regret had better be in terms of some parameters that depend on the scale of the problem. Okay, so that's so A is somehow measuring the scale of the actions. C is measuring the scale of the costs. So C is the maximum L1 norm of any cost vector that could be chosen by the adversary. For the same reason, we need to depend on this. If all the actions stayed the same, but like the costs were all multiplied by 10, the regret would go up by a factor of 10. So we'd better depend on something like this. And R is the maximum cost that can be experienced by the algorithm. So R is the maximum over actions of the learner and costs selected by the adversary of the cost that would be experienced by the algorithm. So A inner product with C. Okay, and epsilon is this parameter that we get to choose. Epsilon is controlling the scale of the noise that we're at. Okay, so epsilon is sort of a parameter that we get to choose. This theorem has 2 terms in it. The first of them is, as we make epsilon smaller and smaller, the first term gets bigger. But as we make epsilon smaller and smaller, the second term gets smaller. So what should we do if we're interested in worst case bounds? We should choose epsilon to balance these 2 terms, right? So if we do that, like choosing epsilon optimally, what we get is that the regret is less than or equal to the square root of 8CART. Okay, so something that grows only with the square root of t, same kind of bounds we got with multiplicative weights. So that's sort of like the right regret bound. And if we sort of see, if we try to instantiate this with like online shortest paths, right? Like, these numbers are going to sort of scale with like d, the number of edges in the graph, because a path or really less than d, only sort of the length of the longest path, but I guess that could be as long as d, which is logarithmic in the number of paths in the graph. Okay, and so we're getting the same kinds of bounds that we would expect from something like multiplicative weights, depending logarithmically on the number of actions with the square root of t. But if you look at the algorithm, there's no explicit dependence on the number of actions. All of the computational action is here. We just need to solve this batch optimization problem. If it's online shortest paths, this is just Dijkstra's algorithm. This is find the shortest path in the graph given costs for each edge. Okay, so this algorithm, follow the perturbed leader, I think the right way to think about it is as a reduction from this more difficult sequential decision problem to sort of just a computational problem, this batch optimization problem, which for online shortest paths is Dijkstra's algorithm. Okay, and this is sort of the best you could hope for in that the online problem is like strictly harder than the batch problem, right? Like in the online problem, I could, if I had some instance of the batch problem I wanted you to solve, I could just give you that instance over and over and over again in the online problem. The only way you could get low regret would be to solve the batch problem. So we can't possibly hope for anything stronger than this, which is an algorithm that is efficient, exactly when the offline problem is efficient. Yeah.
How do you choose epsilon again?
Yeah, so this is our bound in terms of epsilon. If I want to get the best worst case bound, I'm going to set this term equal to this term, and that's how I pick epsilon. Okay.
So what if there was a problem where it's similar to, it's like one action is better than the other, but instead of reversing, it's just always one action is slightly better than the other?
Mm-hmm. Yeah. So then what's going to good. So what's going to happen? So like, first of all, how is epsilon going to be set if I try to balance these two terms? So let's ignore all these funny constants and just think about t.
Yeah.
I'll set epsilon to be like 1 over root t, which means that what I'm doing is I'm looking at the cumulative cost in hindsight, and then I'm adding noise on the order of like root t to each coordinate. Okay. So if one action, like if you were giving me the same instance over and over and over again, I really should have played follow the leader, not follow the leader. Sure, in that case, follow the leader would like get 0 regret. It's not a changing problem. What's going to happen here, because this algorithm is sort of defending against an adversary, and so would do well even if the adversary was doing something more clever. Here, basically, for the first root t rounds, the algorithm would be basically playing uniformly random things because the noise is on the scale of root t. It's going to take like root t rounds before the signal, which is like the accumulated cost, is on the same magnitude as the noise. So for the first root t rounds, roughly speaking, this would just sort of be playing uniformly at random. And after that, it would basically, the signal would be stronger than the noise, and it would basically play the right thing every time. So if you knew that was what was going to happen, you'd pick a larger value of epsilon. Mm-hmm. But right, so this is not setting epsilon in this way. This is not the best way to set epsilon on an instance by instance basis. This is the best way to set epsilon if what you're interested in is the performance on the worst case sequence. Okay. Good question. Other questions? Okay. Cool. So let's remember our plan of attack, which we had started implementing last time. So our long-term goal is to prove this theorem for follow the perturbed leader, or long-term. We're going to do it by the end of the class today. Our goal is to prove this theorem for follow the perturbed leader. But the way we're going to do it is we're going to analyze a series of 3 algorithms that are all similar to one another. The first one is going to have great regret properties. The last one's going to be follow the perturbed leader. And the one in between is going to help us link the performance of the first of these algorithms with the last of them. Okay? So, okay. So the first algorithm in this chain that we're going to analyze is called be the leader. Okay, and all it is follow the leader without noise, except shifted one step into the future. be the leader does today what follow the leader would do tomorrow. Okay, so you can't implement be the leader because, in particular, like one of the things it bases its decision on is what the cost was today. I don't know that at the time I'm making my decision, but if you could implement it, it would have a great regret bound. And the plan of attack is to show that be the leader has this great regret bound. That's step one. Step two is to show that be the perturbed leader is not too bad either. Like if we added noise to be the leader, the regret bound would get worse in some way proportional to the noise, but it wouldn't like drop to zero. And that be the perturbed leader is playing every day almost exactly the same distribution as follow the perturbed leader, because the noise is enough to drown out the contribution of the cost vector at day t in this sum, which is the only difference between be the leader and follow the perturbed leader. And therefore, if be the perturbed leader has a good regret bound and follow the perturbed leader is playing almost the same distribution every round, it must have almost the same regret bound. That's the plan of attack. Okay, so to put the plan into action. Let's see. All right, so what is be the leader? So be the leader just plays every day the action I'll call a hat t. So I'll follow the notational plan of attack. Follow the perturbed leader plays at every day. We're analyzing a sequence of 3 algorithms. Be the perturbed leader will play actions that have hats on. Sorry, be the leader will play actions that have hats on them. Be the perturbed leader will play actions that have twiddles on them. Okay, so be the leader, a hat t. How does it select a hat t? Well, remember, be the leader is just follow the leader, but shifted 1 day backwards. So it's just, shifted 1 day backwards, 1 day forwards. Every day, be the leader plays the action that minimizes amongst all of its actions the cost of that action when played against c less than t plus 1. So this is just the accumulated cost vector from day 1 up through and including today. This is the thing that follow the leader would play tomorrow. We can't actually play it today because this is a sum over t terms. We only know t minus 1 of those terms. The last of those t terms hasn't yet been realized. Okay, but nevertheless, like we can imagine what would happen if we could, and we can analyze what its regret bound would be. And the claim is that its regret bound is great. Its regret is like 0. It doesn't have regret at all to any of the actions. Okay, so what's the claim? Be the leader has non-positive regret. By which I mean, if I look at, if I can compare to any one of the actions that are available to me. If I look at the accumulated cost of be the leader, so the sum over all of the days of a hat t inner product with ct, the cost of be the leader, no matter what happens, no matter what sequence of cost vectors is realized, this is only smaller than the sum over all of the days of the accumulated cost of any fixed action A. Okay, so this is great. Normally we prove this, the difference between this and this, that's the regret of the algorithm to action A. So normally the kind of thing we prove is that the regret to the best action is not 0, it's just like some quantity that's growing sublinearly with t, like root t. Okay? Here, if only we were allowed to cheat by just a little bit and play, what is actually sort of a bad algorithm, like follow the leader, just shifted, allowing it to peak one day into the future, that we would actually have zero regret. Okay, so quite a strong statement. Okay, but the proof is actually quite simple. Okay, we'll prove it by induction. Induction on the time horizon, T. Okay, so the base case is true by definition. So for T equals 1, well, if I just look at the definition of A hat 1, this is the action that minimizes the inner product with C1, because at day 1, the accumulated cost up through and including day 1 is just the cost at day 1. Okay, and so the right-hand side at T equals 1 is just the cost of the action at day 1. And by definition, what Be the Leader is doing at day 1 is just playing the action that minimizes the cost at day 1. So the minimizer is less than anything else. Like at day 1, we're doing exactly the right thing. Okay, by the way, if we did have the ability to look ahead into the future, a much smarter thing to do than play Be the Leader would be to always optimize for today's action. That's not what Be the Leader is doing, but it happens that that's what Be the Leader is doing at day 1. That's why the base case works out. Okay, so now, let's see what happens. Well, we're going to assume that this claim is true up through T equals K, and we're going to see what happens at day K plus 1. Hopefully it's still true at day K plus 1. Okay, well, what is our accumulated cost up through day K plus 1? We know that it's a proof by induction. So a very sensible thing to do as our first maneuver is to separate this out as our accumulated cost up through day K. That's the thing we make an inductive assumption about, and then add on the extra term, which is our cost at day K plus 1. So this is just, this is the sum over K plus 1 terms, which I could write as the sum over the first K terms, the cost of the algorithm over the first K days, plus the cost of the algorithm at day K plus 1. Okay. Now, the cost of the algorithm over the first K terms. This is the thing that I get to make my inductive assumption about. So I know that the accumulated cost of the algorithm over the first K days is at most the accumulated cost of any single one fixed action. Right? That's the inductive assumption. I could apply that to any fixed action, but you know what? Here's a fixed action, like the action that the algorithm plays at day K plus 1. I'll pick that one. So I know amongst many other statements of this form for every other action that's available, the accumulated cost of the algorithm over the first K days is at most what the cost of the algorithm would have been had every single day it played what Be the Leader played at day K plus 1. That's a fixed action. Okay, so this is at most the sum over the first K days of the cost of the fixed action every day playing the fixed action that Be the Leader played at day K plus 1, Okay, this is the induction hypothesis plus the cost that the algorithm experiences at day k plus 1. Okay, but you know, what is this? You know, it's a fixed action now. I'm taking the inner product of this fixed action over the sum of the costs over the first k days, and then also taking the inner product with the same action for the cost at day k plus 1. So this is just the cost of playing this fixed action a at k plus 1 against the accumulated cost vectors, starting from, accumulating them from day 1 up through and including day k plus 1. Okay? But what is be the leader doing? It is choosing the action at day k plus 1 that minimizes this expression. Okay? So this particular action, a hat k plus 1, this is the minimizer for this expression. And so in particular, it's only smaller than the accumulated cost for any other action. Because a hat k plus 1 is the minimizer. Okay, and so that's it. So be the leader has 0 regret, which on the one hand is great. The only possible sticking point is be the leader is impossible to run because it involves looking into the future. So we've got this great algorithm, but we can't run it. What do we do? Okay, but is it clear where we are so far? At this point, we've now caught up to what we did last week and sort of the remaining steps of analysis we haven't seen before. So I want to make sure at this point that I'm going to go a little bit more slowly for the next couple of lemmas because we haven't seen them before, but I want to make sure that everyone's on the same page here. Okay, let me just sort of, yes.
I have an example of what I did.
Yes.
So it feels like there's no other way.
That's right. If you're playing against an adaptive adversary, you must randomize and I say this not facetiously, but basically any question I have about this kind of stuff, I can answer for myself by thinking hard about rock, paper, scissors. Rock, paper, scissors is a special case of this. I've got 3 actions, rock and paper and scissors. The costs are chosen by an adversary. And if I don't randomize and I tell you up front that I'm playing rock, I'm gonna do badly. So you do, to get any kind of regret guarantee in an adversarial setting, randomization is really important. Mm-hmm.
I don't want to jump. But here,
yeah, there are some things in between. And in fact, we've even seen some things like this. So if you remember what we proved about multiplicative weights, the bound we proved before we set the tunable parameter, the equivalent of epsilon here, the learning rate, was in terms of the maximum cost, the cost basically of the best fixed action in hindsight. And so one way to limit the adversary, for example, and this was even, this was the very first algorithm we saw in this class, the halving algorithm was the extreme form of this, is to say that one of the options is pretty good. The adversary must play so that at least one of the actions has loss below some absolute amount. Okay, and so the halving algorithm was able to get regret that didn't grow with t at all when we said there has to be a perfect action. And we saw with multiplicative weights, you could actually sort of replicate that even if the adversary could let the best action make sort of log k many mistakes. And then more generally, the regret bound doesn't have to scale with t. It has to scale with the, basically the accumulated cost of the best action in hindsight. So that's one example. Oh, so I could assume, like I could constrain the adversary to make sure that, there must be one action that never makes more than, 10,000 mistakes or whatever, but such that the costs are not following any distribution. The adversary could like make all 10,000 of those expensive rounds. You could front load them all to try to to try to break algorithms that are relying on statistical assumptions and throwing out actions that perform poorly early on, which would be a fine idea if the costs were drawn IID, but would be a bad idea in this setting. So it is between the statistical and the worst case setting. And there's other things you can imagine doing. So yes, yeah, it's a good question. Even follow the leader. You can prove regret bounds on it in terms of the sequence that arrives, right? Like it has no worst case regret bounds, but in general, its regret will be bounded by the number of times the leader changes. And so it actually does pretty well in a statistical setting. Yes, in fact, maybe we'll see that next time. The thing we just proved is that statement after we rearrange things a little bit. So I'll do that rearranging next class. It'll be useful in the next algorithm we analyze. But yeah, the proof of that is this proof. Cool, yes.
Why are you able to put in k plus 1 into I guess the second line, the less than you said it's an induction?
Oh yeah, so this is the accumulated cost over the first k rounds. The inductive hypothesis is that this bound holds for the first k rounds. So the cost of the algorithm is no more than the cost of any fixed action. And here I'm just choosing the particular fixed action of interest is this thing that is called a hat k plus 1, whatever action the algorithm happens to play around k plus 1.
Oh.
So this sum is not over k, the sum is over t. So this is a fixed action. It's not changing with t.
Got it. Okay.
Make sense?
Yeah, so you define as whatever
it's its definition is the thing that the algorithm plays at around k plus 1. Good. Okay, other questions? All right. Okay, so let's now move on to the next algorithm in this sequence. Okay, so this was be the leader. It was a great algorithm, but we couldn't play it. Let's define a slightly worse algorithm that we also can't play. Okay, it's going to be called be the perturbed leader. And it's the same as be the leader, except with noise. So in the same way that sort of be the leader was just playing follow the leader, but like looking one step into the future, be the perturbed leader is just playing follow the perturbed leader, but looking one step into the future. Okay, so in particular, be the perturbed leader, what's it going to do? Well, it's going to play the action, which I'll now write as a twiddle t, okay? Follow the perturbed leader a t, be the leader a hat t, be the perturbed leader a twiddle t. And what is a twiddle t? It's just the action played by follow the perturbed leader, but sort of one day before follow the perturbed leader does it. So a twiddle t is the action that minimizes overall possible actions. The inner product of A with the accumulated cost vector with one step look ahead, plus a noise random variable, where the noise is sampled in exactly the same way as it is in follow the perturbed leader. So the noise is uniform between 0 and 1 over epsilon in every coordinate. Okay, so is it clear what be the perturbed leader is? Yeah. Yeah, good, although this will be one of the slick moves in the proof. So the noise, indeed, for follow the perturbed leader and for, be the perturbed leader is different at every round. But the thing we are ultimately analyzing is the expected cost of the algorithm, okay? Expectations are linear. They don't care about correlations between rounds. So the expectation of the sum of a bunch of things is the sum of the expectations of those things. And so the expected cost will actually be the same whether or not we freshly randomize at every round or whether we use fixed randomness. And this trick will be important to our analysis. That's right. So there's a little bit of a subtlety in this analysis that we can talk about a little bit, but I'll try not to dwell on too much, which is that to actually run this algorithm and have guarantees, and to actually be an algorithm that falls into the online linear optimization framework I set up, it's important that the randomness you use at day t be independent of the choice of the adversary at day t. Okay, but like the way we set up the online linear optimization problem, what you commit to at day t is a distribution over actions, and then the adversary, as a function of that, chooses a cost, but the adversary cannot look at your random coins and see how you sample from the distribution. So that is important, and that's why the algorithm actually needs to re-randomize at every step to work against an adaptive adversary. But once I fix a sequence of costs, then when I look at in expectation only over the randomness of the algorithm, the cost of the algorithm, the randomness of the algorithm is unchanged whether I sort of use the same realization of noise every single round or whether I re-randomize it every time. Okay, so actually, like, you could actually do that if you were running against a non-adaptive adversary, an adversary who had to fix all of their costs up front. Then you actually wouldn't need to re-randomize every time. The theorem we're going to prove is that simultaneously, for every fixed vector of costs, the expected regret of follow the perturbed leader is small. And if you re-randomize every time and therefore break any correlation between the random coins and the choices of the adversary, the same theorem holds against an adaptive adversary. Does that make sense? Okay, so this is what be the perturbed leader is. Okay, so we know that follow the perturbed leader is great. Be the perturbed leader is somewhat worse, but not that much worse. Okay, so be the perturbed leader has expected regret for every sequence of cost vectors bounded by the following. Okay, so this is going to be for a fixed sequence of cost vectors, so there's no randomness there. The expectation here, the only randomness in be the perturbed leader once I fix the cost vectors is the randomness of the noise that we're adding. So this is an expectation over the random draw of the noise. Okay, so the expected cost of the algorithm cost of be the perturbed leader minus the cost of any fixed action, so the regret to action A. This is at most A over epsilon, where if you remember, A was one of these things that shows up in our final bound. It's the diameter of the action space. It's the worst case L1 norm of the difference between any two actions in our action space. Okay, so be the leader had 0 regret. That's what we just proved. Now we're sort of making the algorithm worse. Like we're needlessly adding noise to it. It already had zero regret before we added the noise. We add the noise, now things are worse. But what we're showing is that they're not that much worse. Like the degree to which we have made the regret bound worse by adding noise can be bounded by the scale of the noise and something about the scale of the actions. Yeah. There is no t in it. Although eventually we are going to set epsilon to be something like 1 over root t. But yes, there's no t in this bound, which would be surprising at first, except before we added the noise, there was no anything in it. It was regret 0. So remember, this is still an impossible algorithm to run because it's looking one day in the future. So we're still getting a regret bound that is better than we could actually hope for. In particular, it's independent of t. Like in particular, here you just want to set epsilon to be as big as possible, right? Like we sort of know if you don't add any noise at all, which sort of corresponds to setting epsilon tending towards infinity, that there's regret 0. So this is entirely consistent with that. Like if you set epsilon tending towards infinity, you recover, be the leader, and no regret. And if you add, constant amounts of noise, only constant regret. Other questions about the statement? Okay, so we started with a really good but impossible to run algorithm. What we've done is we've sort of jiggled it around. We've added noise to it. It's still impossible to run, but now it's worse. Like now it has positive regret, but it's not unboundedly worse. We can control how much worse it is by how much noise we add. If we only add a little bit of noise, it's only a little bit worse. Is that clear? Yeah.
I guess the diameter. Why isn't it not the number of actions?
Yeah, I mean, so okay, we'll see in the proof, but intuitively, right? Like what's happening in the algorithm? Like we're sort of adding noise to this vector of costs, and somehow somewhere in here, I guess, we're going to take the inner product of the actions of this noise vector. And so intuitively, should we think of some amount of noise as a little noise or a lot of noise? Kind of depends on the scale of the problem.
But is this for when that number of actions is way too large, so you have to look at a low dimensional thing?
Or I guess I mean ultimately, what are we doing? We're picking the action that has the highest or lowest cost as measured in this way. How much additional, but now we're sort of somehow adding noise to the costs of the actions and picking the one that has lowest cost. Well, how much noise are we adding to the costs of the actions? Well, the amount of noise we're adding to the costs of each action is the inner product with of the action with the noise vector. And so the amount of noise we're adding to that cost depends somehow on the scale of the action vector.
But the action vector scale is d-dimensional, right?
So
max.
Oh, so if all of the costs were between 0 and 1, then this thing would be at most, this A thing would be at most D. But if the costs are between 0 and 100, it could be 100 D. But
oh, okay. So
but if all the costs are between 0 and 1, then yeah, this is at most D. If you want to think of this as D, then
what's the advantage of having costs not be between 0 and 1 or actions not be between? Can't you always scale everything down to be in the 0 to 1?
You could, yeah. It might just be sort of a annoying way to represent things. For example, it's natural to represent paths as the indicator for the edges they contain, whereas otherwise I'd be representing them as some fractional quantity where I'm dividing by the length of the largest path. But yeah, you could get you could equivalently assume all of these quantities were scaled to be 1, and then get prove a bound, and then recover these things through scaling arguments. Good. Okay. Other questions? Okay. All right, so we're going to perform a little bit of sleight of hand that we already discussed. Okay, so as defined, we are perturbing each action with a different noise vector every time. Now, what is the thing we're trying to bound? It is the expected cost of the algorithm. Okay, this is an expectation over a sum of terms. So this is an expectation over, and the randomness here is over t noise random variables. But expectations are linear. So equivalently, this is the sum of the expectation of each term. Now, all of these terms, all of the noise, right? So each expectation, the expectation of each term, t, is an expectation taken over n t plus 1, a different random variable. But they're all identically distributed. They're all uniform. They're all uniformly random variables. And so when we're computing that expectation, we're just summing up the expectations of the individual terms. The correlations between these random variables just don't come up. And so we can equivalently imagine that the algorithm samples a single noise random variable n, uses that every single round. It is a different algorithm, strictly speaking, but it has the same expected cost by linearity of expectation. Okay, does that make sense? This sleight of hand is going to make our lives a lot easier. It's going to make the analysis a lot easier. And it's legal because we're only proving something about the expectation. Is that clear? Okay. So by linearity of expectation, we'll assume that all of the noise random variables are the same. They're each, this single random variable is still distributed as before. It's still a vector of length d in which each coordinate is uniform between 0 and 1 over epsilon. But now we've sort of coupled the noise at each round. So the noise is all the same. Okay, so what is this sleight of hand bias? Well, what it buys us is that we be the perturbed leader. We can now think of it as just being an instance of be the leader in which there's a fictitious round 0 in which the cost was the noise, right? Because what are we optimizing for? It's the sum of the costs of the days from costs from days 1 through t plus 1 plus this noise vector. That's the same as the sum of the costs of days 0 through t, where we just define the cost at day 0 to be the noise vector. Okay. So so be the perturbed leader is be the leader with a round 0 where the cost at round 0 is n, this noise random variable, right? Just to sort of confirm, what is, if we imagine that there's a fake round 0, what is be the leader going to do? What it's going to do is at day t, it's going to play the thing that minimizes overall A, the inner product of A with the sum over all of the rounds of the cost of that round, okay, plus the cost at round 0, which is just n, which is, and this is what Be the Perturbed Leader does. Okay, so does that make sense? Like if we're at, if the noise every round is the same, that means that minimizing costs according to the sum over all of the cost vectors from day 1 through t plus the noise is the same as minimizing cost over the sum of all cost vectors from day 0 to t if we just define the cost at day 0 to be the noise. Okay. Why is this useful? Well, we know a regret bound for Be the Leader. Maybe I just erased it, but this is an easy regret bound to remember. The regret bound for Be the Leader is 0. Okay, so we can apply that. We can apply that statement we've already proven to this sort of hypothetical version of Be the Leader that has a round 0. Okay, so what do we know from the lemma we just proved? We know that if we look at the accumulated cost of Be the Leader, where now we have to take into account the fictitious round 0, so the cost from day 0 to t of a twiddle t inner product with ct compared to the cost of the best fixed action, again, where we're having to account for this sort of fictitious round 0, where the cost at round 0 is the noise. We know that accounting for this fictitious round 0, the regret of Be the Leader is 0. Now, this is not the thing we want to bound, because this, in this expression, both in accounting for the cost of our algorithm and in accounting for the cost of our benchmark A, we're including this fictitious round 0 in which the costs were noise. And this is just sort of something we're sort of imagining for the purposes of the analysis. That's not the thing we're trying to prove the theorem about. And so, like what's the thing we're trying to prove the theorem about? Well, it's like the same expression except without round 0. So we need to, there's basically 2 extra terms on the left-hand side here than we want. The round 0 cost for our algorithm and the round 0 cost for our benchmark A. And we need to get rid of those. We need to move those to the right-hand side. Okay? But that's easy. It's literally just 2 terms, right? The inner product of A0 with C0 and the inner product of A with C0. Okay, so we can do that. The thing we actually want to bound, which is the regret over the real rounds, the sum over all of the rounds from days 1 through t of the inner product of the algorithm, of the action we choose, and the cost at day t, minus the cost of action A at day t. This, well, is bounded by the inner product of A minus a twiddle 0 with the cost at round 0, which is, remember, just the noise. Okay, like all that's happened here is we applied our lemma to Be the Leader with this fictitious round 0. That wasn't actually the thing we wanted to bound because round 0 was fictitious. So the two terms that showed up in these two sums corresponding to the cost at round zero, we just move them to the right-hand side. And this term, what's left, where now we're just looking at the cost of the algorithm from days 1 through t, that's the thing we actually want to bound. Okay? So all that remains is, so our regret of be the perturbed leader, it's just the inner product between a vector that corresponds to the difference between two of our actions and this cost vector in which every coordinate is bounded between 0 and 1 over epsilon. Okay? And so all that remains is to bound this, this term. Okay, so our regret, we know, is bounded by the inner product of the difference between A and A twiddle 0 and C0, which is just N. Okay? But, I can sort of bound an inner product in terms of, if I'm taking the inner product between like A and B, I can bound the scale of that inner product by, like the norm of A times the norm of B measured with respect to any pair of dual norms. And like the L1 norm and the L infinity norm are dual norms. So this, right, this is always at most, just as just a property of inner products. This is at most the L1 norm of the first vector, the difference between these two vectors, the difference between these two actions in L1 norm, and the L infinity norm of the noise vector. And what's this? Well, the first thing by definition is upper bounded by A. A is was defined to be the maximum of this quantity over any two pairs of actions in the action set. That's why we defined it that way. And what's the L infinity norm of the noise vector? Well, every coordinate is between 0 and 1 over epsilon, so it's at most 1 over epsilon. And so the regret is at most A over epsilon, and that's it. Okay, so this proof was sort of maybe a little bit too slick, right? There were like a couple tricks, like we sort of said, okay, well, we're bounding the expectation, so like, the expectation doesn't care if we independently randomize at every round or if we couple all of the randomness. And then once we couple all of the randomness, we can imagine that we just sampled it once up front at day 0, and in fact view that as follow the leader starting from day 0, which let us reuse our first lemma, get this sort of regret bound of 0 for the sequence of days starting at this fictitious round 0. And then the final regret bound just sort of corresponds to the error that showed up in our calculation because we were sort of hallucinating this day 0. The contribution of day 0 to like our perfect regret bound was at most A over epsilon. Okay, so we've got what we've shown so far is that adding noise to be the leader doesn't hurt too much. Okay, it hurts sort of in proportion to sort of the scale of the noise, but that's it. Okay. That's right. The statement is true for any fixed set of cost vectors. And the sort of that's where when you're thinking about the fact for why you can't actually correlate all of the randomness when you're actually running the algorithm against an adaptive adversary, that's where the catch is. Like against an adversary, it's not a fixed set of cost vectors. Okay. Okay, so there's one more thing to do. We want to show that the cost of follow the perturbed leader is close to the cost of be the perturbed leader. I think the intuition is sort of straightforward, but there's something to prove. So what is the intuition? Like follow the perturbed leader and be the perturbed leader are sort of solving the same kind of optimization problem. They're taking, they're picking the action that minimizes the inner product with some vector. That vector for both of the algorithms is a random variable. Okay, so like be the perturbed leader, follow the perturbed leader are deterministic algorithms as a function of the vector. All of the randomness comes from the fact that the vector we are optimizing for, that we're solving this linear optimization for, is random. It's a random variable. So the thing we want to prove, first of all, the thing we want to prove is that the distribution on actions induced by follow the perturbed leader every round is close to the distribution on actions induced by be the perturbed leader. If they play very similar distributions, they'll have very similar costs. The way we're going to do that is we're going to show that the distribution on this cost vector as a random variable is close to the distribution on this cost vector as a random variable. If we can do that, we're done, because the action taken by these algorithms is a deterministic post-processing of this noisy cost vector. How are we going to do that? Well, we're going to say, look, this accumulated sum and this accumulated sum differ in only one term. One of them is summing over t minus 1 rounds, the other one summing over t rounds. So they're sort of close in parameter space. They differ in sort of one cost vector. Adding noise to two vectors that are like close in parameter space is going to like make them close in distribution. If you've thought at all about differential privacy, this is what noise is doing in differential privacy. It's doing exactly the same thing here. Okay, so we're going to like be adding noise that is sufficient to like swamp out the difference between these two cost vectors. These cost vectors are accumulating costs over t rounds. So the reason why we can do this without totally destroying the signal is we only need to swamp out with the noise the contribution of a single cost vector, but that's going to be relatively small compared to the accumulation of t cost vectors if t is something big. Okay, that's the intuition. Yeah.
We saw that the follow the leader, follow the
Yeah.
But the thing is, let's say you want to design a math analysis. So we know that like in that scenario there is no actual adversary to actually design the problem, right? Probably follows like a distribution, but because the distribution is very complex, it's hard to.
Well, so let me just maybe like interject with sort of a point of philosophy about analyzing things in the presence of an adversary. The point isn't that we sort of believe, well, okay, maybe sometimes when we use it to like play games, there is an adversary. But in general, we don't really believe there's an adversary out there. What we believe is that we don't understand the model. So for traffic, it's not that the traffic is drawn IID from some distribution. There's some complicated process involving lots of people and holidays and weather, and it's just hard to predict.
But like anyway, so there is no actual adversary. So the thing is, my question is that maybe an example that we know for follow the leader was two adversarial equivalents that is not really applicable in practice. So for me, it's not entirely obvious. Like, I don't know, for example, I'm not designing a map navigator, maybe follow the leader itself.
That's true, and it can be. So and by the way, like, and we'll sort of point this out explicitly next time. Follow the leader has a regret bound. The regret bound to follow the leader is equal to, or is at most the number of times the leader changes. So what this would be in like a navigation scenario is every day you compute the sort of shortest route from your home to Penn, and the leader has changed if the path suggested today is different than the path suggested yesterday. If that doesn't happen that often, if usually it suggests exactly the same path, follow the leader actually has a good regret bound. And so, and similarly, if you know or suspect because of historical data that sort of the switching time is small, like the leader doesn't change that often, you don't have to set epsilon to be as large. So you're right that we're sort of tuning the noise we're adding and therefore finding bounds that are optimized for worst case adversaries. But the same techniques sort of let you take advantage of the fact that your instances might be nice in various ways. And in particular, if the same solution is optimal most days, you can prove theorems by adding less or even no noise.
So like there are some like concrete applications that follow the perturbed leader. I mean, I'm talking about impact.
Yeah, so basically one thing we're gonna, well, so, okay, so like follow leaders actually often works in practice, but one of the things we're gonna use follow the perturbed leader for eventually is computing equilibria in large zero-sum games. There you really are playing against an adversary who is literally trying to maximize your cost at every round. There you want these kinds of worst case regret guarantees. But yes, like in practice, I would not recommend adding as much noise as the theory suggests. Probably the optimal thing to do in practice is to add a smaller amount of noise, possibly no noise, but maybe a little bit of noise is good, but less than this. Yeah.
One of the leaders can't do like I can have overall instances for an expectation. I think it should follow the data never got better so that rearranging of the series. Because it's not tell you that sometimes follow the data can do better, but it can't do like linearly better than follow the data.
That's right. Yeah. So since follow the perturbed leader is never has accumulated loss more than the best in hindsight plus root t, and follow the leader is never better than the best in hindsight, the gap between these two things is at most root t. But root t can matter in practice. So basically, like, this is sort of a general phenomena. Like all the algorithms we've seen so far have some hyperparameter. Usually, like here it's the amount of noise. When we are proving these theorems, we are optimizing that hyperparameter to prove the best worst case bound. But that should not be taken as guidance for how to set. That might not be the optimal hyperparameter setting in your application. And one of the hyperparameter settings is don't add any noise. Okay. Okay. So we're going to look at the distribution of the noisy vectors we're optimizing for in Be the Perturbed Leader and Follow the Perturbed Leader. So let's give them names. Let's say that, okay, first of all, let's say that NT and NT twiddle are the noise vectors used in Follow the Perturbed Leader and Be the Perturbed Leader. So they're just, both of them are sort of independently drawn from the uniform distribution on the support between 0 and 1 over epsilon. These are d-dimensional vectors. Let's say that PT is the vector that Follow the Perturbed Leader is optimizing for. So PT is C less than T, the accumulated costs up through, but not including round T, plus noise. And P twiddle T is the vector of cost that Be the Perturbed Leader is optimizing for. So the accumulated costs up through and including round T plus noise. Okay, And so we want to argue that these two vectors are distributed similarly. So the first observation is that, let's just like write down a little bit more explicitly how these vectors are distributed. So first of all, PT is uniformly distributed in the rectangle that is sort of C less than T plus 0, 1 over epsilon to the D. So basically, start with the vector that is the accumulated costs. In every coordinate, like extend that vector upwards by 1 over epsilon. Okay, that gives you some rectangle. And PT is uniformly distributed in this rectangle. Okay, that's just a rephrasing of this. We're adding uniform random noise to this accumulated vector. Similarly, P twiddle T is uniformly distributed in the rectangle that starts as the vector C less than T plus 1, the accumulated costs up through and including round T, plus the ability to move up or down by 1 over epsilon in every coordinate. Okay, so these are two uniformly distributed random variables where sort of like the starting point differs by by a shift of a single cost vector. Okay, and so the first lemma is that these two regions in which our cost vectors are uniformly distributed, they have large overlap. Okay, so let's say that OT, O for overlap, is the intersection of the first region, C less than T, plus the rectangle of diameter 1 over epsilon, the intersection of that region with the second region, C less than T plus 1, plus the diameter 1 over epsilon rectangle. Okay. The claim is that the probability that follow the perturbed leaders vector does not fall into this overlap region is small. It's less than C times epsilon. And similarly, the probability that B, the perturbed leaders vector, does not fall into this overlap region is small. And if you remember, C is just the maximum L1 norm of any of the cost vectors. Okay, so the claim is that if epsilon is small, then the probability that when we sample a random vector with either follow the perturbed leader or follow the leader, the probability that we don't end up in this overlap region is small. Well, this is just a calculation. What's the probability that we don't end up in this overlap region? Well, it's just the probability that the noise we sample is not in the rectangle that is lower bounded by CT, the cost vector realized at round t. And has width 1 over epsilon. Okay, so like if the noise vector is sampled in this region, then you're going to be in the overlap region because CT is the difference between C less than T and C less than T plus 1. So the only way you're not in the overlap region is if the noise vector doesn't fall into this region. Well, the noise vector is a d-dimensional vector. So what's the chance that the whole vector doesn't fall into this region? It's at most the sum over all of the coordinates that the ith coordinate of the noise vector doesn't fall into the ith coordinate of this region, isn't between CIT, the ith coordinate of the cost vector at round t, and 1 over epsilon plus CIT. Okay. But this is a uniformly drawn random variable. It's uniformly random between 0 and 1 over epsilon. So what's the chance that it doesn't fall into an interval that looks like this? Well, it's at most, for each coordinate, the magnitude of this term, CIT, times epsilon, which is epsilon times the L1 norm of the cost vector at day t, which is upper bounded by epsilon times c. That's the definition of c. It's an upper bound on the L1 norm of the cost vector. Okay. We've got 1 minute left. So let me just tell you how this lemma proves the theorem. It's just a calculation from here on out. Okay, what's going on? Both of these algorithms, Follow the Perturbed Leader and Be the Perturbed Leader, are optimizing, are solving a linear optimization problem for this vector valued random variable that is uniformly distributed and such that both of these vectors, the one for Follow the Perturbed Leader and the one for Be the Perturbed Leader, have a high chance of falling in the overlap region. Well, how is a uniformly random variable distributed conditional on falling into some region? It's just distributed uniformly within that region. So that means that conditional on this vector of costs that these algorithms are optimizing for, falling into the intersection region, the vector of costs is distributed uniformly within the intersection region. That means in particular that it's distributed exactly the same way for Follow the Perturbed Leader and Be the Perturbed Leader. So Follow the Perturbed Leader and Be the Perturbed Leader are optimizing for these random variables that very frequently fall into this fixed region, the overlap region. And when they do fall into that region, they have exactly the same distribution, whether you're playing Follow the Perturbed Leader or Be the Perturbed Leader. Well, that means that when they fall into that region, conditional on falling into that region, Be the Perturbed Leader and Follow the Perturbed Leader have exactly the same expected cost because they're optimizing for exactly the same random variable. They differ only when either PT or P hat T do not fall into this region. But the probability that they don't fall into this region is small, and therefore the contribution to the expected cost that the rounds for which these vectors don't fall into the overlap region is correspondingly small. Okay? So we already have a regret bound for Be the Perturbed Leader. And now we know that the regret for Follow the Perturbed Leader is at most the regret for Be the Perturbed Leader plus C epsilon, the probability that these algorithms are actually sort of optimizing for a vector that is distributed differently. Okay, there's a formal version of that lemma in the notes. If that was confusing, it's all written down. But morally, that's what's going on. We've already done all of the hard parts. all that is left is to observe that, like, if I've got two random variables that are almost always distributed the same way, then any expectation I take over those random variables must be close. And so we know that the expected regret for be the perturbed leader is small. We proved that. This argument shows that the expected regret for follow the perturbed leader is also small. Okay? We finished follow the perturbed leader. Next time is something else. See you guys on Monday.